Good afternoon. Good afternoon. Probably now it is better. These are interesting and dangerous time, and I never expected that I will give talk from basement of my house. But for the moment, it is not needed. So we'll continue our story of plain graphs and not diagrams. And the first part of today's talk will be about history. And when I should still comment that I say not, really I mean not or links. And as you know, as we discussed last time, when we consider more than one component, like this red one and this colorful one, yellow one, this is a link of two components, two pieces of string. So we should consider them as well. Still, generic term is not, but we say link of some number of components and not as one component. And you see, this is non-trivial link. To break this, I have to do illegal operation, cut it, and then maybe a glue, but I will use this as a pointer. So, last time I mentioned that the first mathematician who mentioned knots as part of mathematics was Vandermonde in the paper of 1771. However, he just mentioned knots, nets, blades with respect to geometry as situs of Leibniz. As many topics, disciplines of mathematics, we can say that it was Carl Friedrich Gauss who was the first person to consider seriously mathematical knots. However, he was perfectionist and he never wrote something he was unsure or couldn't do precisely, so his work on knot theory was only preserved in his notebooks. Plenty of his notebooks are now in old library in Göttingen. So when you look through these notebooks, you can see his drawings, sometimes with comment, sometimes without comment. So now personal history, I went to this old library in Göttingen in 1995, and to my surprise, they let me to go through Gauss notebooks and a lot of interesting things. So Gauss first time drawing his notebooks, not when he was 17 years old, in 1794. So still 18th century, but of course more than 20 years after Vandermonde. The first person who wrote really about knots and wrote even booklet devoted partial to knots was Gauss' student Johann Benedict Listing. Listing parents were poor parents. They emigrated from Bohemia and settled in what is now Germany. And he was initially studying in Frankfurt. So another personal notes, I was meeting well-known mathematician from Frankfurt called Burde. And Burde, I asked Burde, and Burde took me to old gymnasium of Listing. Building didn't exist, but there was new building, and they still were keeping his book from the school, his grades and his behavior, etc. So this is about Listing, and Listing wrote this booklet, so I will talk about Listing more probably later. Then somehow in Germany, knot theory was not done. There was no immediate followers of Gauss and Listing. And as I was mentioning last time, really we should go to Scotland. I was telling about Kelvin idea of atoms as knots in ether, vortex line in ether. So this was Thomson, later Lord Kelvin, and he was motivated by his friend Peter Guthrie Tait, work, his smoking rings, behaving kind of in stable way, and he asked him to make tables of atoms, tables of knots. He started only 10 years later, and he spent almost 30 years of his life working on them. Could not be 30 because he died in 1901. And I didn't mention this last time, but Tait was really motivated by the work of famous German physicist Hermann von Helmholtz, because it was Helmholtz who noticed that kind of vortex lines are stable. They either form closed lines, or maybe they go from one boundary to another boundary. And it motivated Tait to make experiments with smoking rings, and then Kelvin to have atomic theory. In the background was always Maxwell, who was very well informed. knew about work of listing, and in fact he told Tate about work of listing, and Tate was often writing to Maxwell, and they were exchanging ideas. Except that Maxwell never published about knots, and we know about this only, about his serious work on knots only maybe 15 or 20 years ago, when his manuscripts were partially published. So this is more or less history for today. We'll talk about Tate construction. So I wrote here from graphs to knots, but in fact it's very important to go back. We don't spend much time, but some people think that the main idea which we now use from Tate is that we draw a diagram like this, and then we find the graph like this triangle, so go in the opposite direction. So this will be the second part of this talk, less history, and I will start from showing how to solve homeworks I gave, and we'll go further with these drawings. So thank you. The second part of our talk will be practical drawing of what we should now call Tate graphs. So once more to stress that it was already in the first paper of Tate in 1877, when he was trying to draw tables of knots and links, he was using graphs in the background and drawing knot on them. So let's remind you convention. So whenever we have edge of the graph, then we draw the crossing, and it's very important to show which arc is on the top and which arc is at the bottom. So I can comment that few people sent me homework and they didn't do this distinguish. It's very important because otherwise we lose 3D structure of the knot. In the knot, something should be over, something should be under. So this was convention, and we're trying to remember how to remember this convention. And one suggestion was that we walk along an edge and the bridge is always on the left. So this allows us to draw it quickly, even if position is different. We walk along the edge and bridge is on the left. And of course tunnel on the left. However, some other people suggested different method of remembering this. These people who still remember what is right-hand screw will see that really we use here right-hand screw. We have this screw along edge, and then we see that it's twisted like this. Twisted like this. Or if you go from other direction, twisted like this, so it's always the same. So this is how we remember. So we can go, I will keep for a moment convention, but let's go to 3 plain graphs which I gave for homework. First of them was just square with diagonal. So let's draw this. So we use our method, whatever bridge on the left, or just remembering how it is. So first crossings. Bridge on the left. So this is the first stage of drawing the diagram, but we should now connect this. We have these loose ends, we go along edges or walls, as I prefer to say, and connect them. So for example, here we go along wall and connect. Connect along wall, so be careful along wall. Okay, everything is connected. So now we can count number of components. That is relatively easy, but again, I should say that some people who did it as homework, when they were counting number of components, they destroyed crossings, and this is not good. Crossings are very important, and we just use different color to see how many components we have. So for example, we start in any place. We follow. Here was over, so we can go over, but here was under. So it was under and going to the other side. Clearly this is the first component. Then I will not draw, but clearly this red one is second component. I can mention something which I stressed last time, that when we start from plane graph and draw diagram is always alternating. Over, under. This is good way of checking whether you didn't make mistake, because it's enough to have one crossing correct and then should be alternating. Over, under, same in this component. Under, over, under. So this is a link of two components. In fact, this link has name. First, like Tate would call them, it has 5 crossings, 5 edges, so it is 5. Then it is link of two components. So we put 2 on the top. And in tables of Tate, it is the first, and in fact, it is up to mirror image, it is the only, and in fact, there is the only link of two components which is non-trivial. So he put 1. So this is one thing. Then, always I would suggest write that is link of two components. Link of two components. And this link was used in the very substantial way by Whitehead. So very often it is called Whitehead link. Mathematician, non-trivial way, Whitehead link. On the other hand, but it was called Whitehead link, was not well known, this link is used as well by Maxwell. And he's illustrating the fact that really there is no linking number, even if it is very complicated, there is no linking number between these things with proper definition. But we call this Whitehead link, not Maxwell link. So what was the second link which was in Homburg? This was link of the graph which is K-fold. So we look for the diagram of K-fold. Just to recall, K-fold or K in general, K-fold is the graph with 4 vertices, and every pair of different vertices is connected by exactly 1 edge. So what is this? We can of course draw this. Maybe it would be nicer to have bigger picture, but maybe that's enough. Let's start with red. Okay, bridge on the left. Bridge on the left. So we have all crossings. We know which is over, which is under. Now we should be very careful when we connect this, not to make mistake. For example, looks like maybe it's closer here than here, but we know we should go along walls. Along wall. That's easy, along wall. But here we should do it carefully. Was not obvious, but this is our picture. Now we should count number of components. So I will change color and try to see. So how I'm checking this? In fact, you can ask me, I draw the plane graph and you ask me, can I say immediately how many components it has? No, immediately no. There are various criteria, but I think the quickest and the easiest is just to draw the diagram. And then you see how many components. Okay. So let's say this was red, so let's say something here. Let's try this blue. Blue. We don't destroy crossing. Okay, so we see this is the blue one. Over, under. So it is alternating. So we need one more color. I don't think that yellow is visible. Maybe this. Now it will be too similar. Let's try yellow. It should be yellow, and I hope we'll see. So this will be yellow.
Very good.
It is visible, very good. Okay, that's it, yellow. And then clearly you can see that the red one will be the third one. So it has 3 components. So let's write this. 3 component. we use shorter notation, we write number of component of the diagram of our link K4. So this is equal to 3. Link of 3 components. This link has very old name because it was used, such a link was used as the coat of arms in Borromeus family Italy in Renaissance. So because of this, it's very often, in fact, always called Borromean links. This link is Borromean. What about atomic notation, like Tate started? This is of 6 edges, 6 crossings. So this clearly will be 6. It has 3 components. And in the tables, it is the second. So Borromean ring is the second in the tables. So you can ask justly what is the first. And I remember, so let's draw the first. So let's erase Peter Guthrie Tate, know about him. The next one is really triangle with every edge doubled, coming from such a graph. So this is the plain graph, and now we have to draw link. I already told that it will be link of 3 components, but let's check. So first, crossings, bridge on the left, or use right screw technique. I hope you can see something. So we have all crossings, now we have to connect them. So then outside is easy connection. But inside we should be careful. We go along wall, so I can even overstate this. But it's not so difficult. Okay. There are kind of 3 rings connected, one with next one, with next one, with next one around. But still that counts number of components precisely. I will keep this red one fixed. So this is the blue component, and let's do yellow component on this side. Yellow component. So you see it has 3 components. There's red on the top, yellow on the left, and blue on the right. And what is the name in Tate notation? It has still 6 crossings, 3 components, and as I was telling, this was taught by Tate simpler than Borromean rings, so this is the first. So we have 613 and 623 Borromean ring. There was one more given as homework. I will erase this because this will be family of graphs, plain graphs, for which we'll spend more time today partially and then next class. So let's erase this one. So what was next one? Was just this. Square with kind of like this, so or maybe you can say hexagon with this diagonal. So let's see what is the picture. This is rather well-known knot. I think in Buddhist culture in Tibet. India. We did see when we were in Nepal, we did see this very often with some decorations, but essentially this link. So we have every crossing for every edge, and now we connect along lines. So this is our knot. It is a knot. Let's check this. I will start going from some place and follow, not destroying crossings, of course. It's alternating. It's clearly a knot. So, as I said, we'll consider this, so this a knot. Let's just comment a knot, or link of one component. So now we'll study playing graphs and knots or links related with such diagrams. So what will be our general setting? It will be graph, which I call grid graph. G with two parameters M and N. Let me erase Borromean links. So what is grid graph GMN? We just take box, makes M squares here, divide this into M rows and N columns. So I'm just drawing example. So how many rows we have? 1, 2, 3, 4, 5. So this will be G5. And how many columns? 1, 2, 3, 4, 5, 6. So this is 5, 6. You can treat it as homework, draw this nice. It will be, in fact, knot with many, many crossings. Of course, we can, without effort, I think we did in class count how many edges has such G5, 6, or generally GMN. But today, and in fact it was partially homework was this, and then you can try to find number of components. So big question, and I will come back to this, how many components has diagram of this grid graph. But today, let's concentrate on just one row. So our question will be find number of components of G1n, of diagram of G1n. The diagram of G1n. So let me erase general grid graph. So question. So just as this exercise I will do. Now we'll find pattern or formula, and as a homework we'll do similar thing for 2. Let me erase this was general. So grid graphs. Okay, so let's do this. This is, in our language, a graph was G1, 2. So we have to see what is G1, 0 and G1, 1. And maybe then go further to G2, 2, G3, 2, and maybe one more. So this is maybe tricky. What is G1, 1? Because there is no column square. But that's not so difficult. It will be just like this. 1 row, 0 columns. And what will be G1, 1? G1, 1 is simple as well. Already we discussed this, but it's square. But let's do this. See how many components they have. So, bridge on the left. Of course, there is a knot. Trivial knot, in fact, we can undo this. For the square, you already knew it is polygon with even number of edges. So we expect link of 2 components, but let's repeat this. And let's stress these two components, so that one of them will be blue. Okay. So a link of two components. Let me write two components. For a knot is one component. Let's stress this. For G12 is a knot, one component. Okay, what we get for, let me erase this main question for us. Maybe it should be somewhere written only with small letters. We ask, what is the number of components today of diagram of grid graph G1N, general N. We'll guess the pattern. So next, G13. This is G13, and now let's draw diagram. Bridge on the left. We have our, how many crossings it has? 3, 6, 10. Okay, let's connect them. Let's connect loose ends of crossings along walls. Everything is connected. Already when we build these bigger and bigger diagrams, one can comment that some people suspect that Celts were masters of drawing knots in art and in symbolic religious things. Then maybe they were using underlining pieces of graph to have very complicated knot. Piece graph here, 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 and you can have very complicated knotting rather easily done. So now our task is to find number of components. So let's take this top to check how far it goes as one component. That's it. So this is one component. Probably you can see already that the rest is second component. Very symmetric to this, but let's still check this. Yes. So this is two components. Once more stress that we were checking how many components. One should not destroy crossings, because then we lose information. So it happens that it's a link of two components. Link of two components. So how many components we have? One component, two components. One component, two components. Looks like pattern. 1, 2, 1, 2. Let's check this for the next example, and we expect that will be a knot, a link of one component. So we check G14. So a lot of drawing. It will be the last drawing I do today, last complete drawing I do today. So let's try. Bridge on the left. And now we have to connect. Oh, I didn't finish. I didn't connect, of course. Connections are not on the now. One should be careful. We go along walls. We don't jump like here, looks like clocks. We go along wall. So this is a very nice, symmetric, full picture. So we suspect that this is a knot. I will just follow this by red pen with any place we can start. If we check whether there is one piece of rope or more. Okay, let's start here. Don't destroy it, crossing. Okay, go and go, and we are almost done. It was only one component. So a knot or link of one component. A knot, which means link of one component. So we have pattern. Pattern was we started from 1, 2, 1, 2, 1, and we can predict that it will continue 1, 2, 1, 2, 1, 2. We can try to write this as well as the formula. So what will be the formula? Remember that this one was corresponding to n equal 0, n equal 0, n equal 1, n equal 2, n equal 3, and finally n equal 4, etc. So we can see that for n even, it is a knot, and for n odd, it has two components. So we observe, we don't prove anything, but we observe, so let's call this fact, or observation, that our number of components of diagram of G1n is equal either 1 or 2, and 1 if when it was 1, when n was even, if n even, and 2 if n is odd. So this is kind of solved. We don't prove in this class anything in this lecture, but you can see from pattern. So what will be homework? Homework will be to do the same thing, but with G1, G2n. Draw G2n for many n, for n equals 0, 1, 2, 3, at least 4, maybe 5 I prefer, at home, and find pattern for the number of components. I will erase this and write homework once more. I will have to erase this nice diagram. No. Diagrams. For I mean link diagrams, maybe I should not write for, just the grid graph 2n for n and some reasonable number for n equals 0, 1, 2, 3, 4, I think 5 to have pattern, then we'll be sure. How many components? Fine. So find number of components in these cases. color each component by different color and look for a pattern or maybe even better, find a formula or the formula for number of components of the diagram of G2n. So send me good solutions, and eventually we try to work with GMN. If you're ambitious immediately, find number of components of the diagram of grid graph GMN. But for looking for patterns, let's do first G2n. We did G1. So that's enough for today. Thank you. Have a good afternoon.